Look out at the global ocean on any given day, and you are watching the arteries of human civilization at work. International shipping seamlessly moves 90% of all global commerce, transporting everything from raw iron ore to the digital device you're watching this on. But dragging millions of tons of steel through heavy saltwater requires an immense amount of energy. To maintain that logistical triumph, the global merchant fleet produces a climate footprint roughly equal to the entire global aviation industry. To understand the magnitude of those emissions, look at this data ranking global carbon emitters. If the international shipping industry were an independent sovereign nation, it would rank as the world's sixth largest polluter. Recognizing the scale of this environmental cost, the specialized UN agency that regulates seaborne trade, the International Maritime Organization, or IMO, stepped in. They established a definitive mandate. International shipping must achieve net zero emissions by the year 2050. Moving from the sail to the steam engine took over a century. This mandate requires a transition from heavy diesel to zero-carbon propulsion in less than 30 years, requiring engineers to integrate high-density energy storage and synthetic fuel systems into the basic structural design of every new hull. The clock is already working against them because of the economic reality of fleet lock-in. Commercial vessels are expensive assets designed to operate for over 2 decades. A heavy fuel ship constructed today will remain an active polluter well into the mid-century. This leaves no room for a gradual transition. Every vessel laid down in a shipyard this year determines the emission profile of the global fleet for the next quarter century. Net Zero 2050 represents a physical construction deadline. Solving the engineering challenges of zero-emission design must happen on the dry dock today. Navigating toward that solution starts deep within the engine room, where engineers face the fuel trilemma. Every power source they choose requires balancing 3 constraints: fuel availability, economic cost, and operational safety. For years, liquefied natural gas served as a transitional bridge. It burns cleaner than diesel, but looking at this diagram, we can see its flaw: methane slip. Because methane is 20 times more potent as a greenhouse gas than carbon dioxide, even minor leaks during combustion negate the environmental benefits of the fuel. To eliminate carbon, the industry is scaling up chemical alternatives. They are testing green methanol, engineering hydrogen fuel cells that exhaust only pure water vapor, and designing specialized engines to burn ammonia, a carbon-free, highly energy-dense chemical. On the furthest edge of this frontier, naval architects are returning to the atom. They are exploring the integration of small modular reactors, compact nuclear power plants designed to be lowered into the hull, offering decades of zero-emission energy. Conquering the chemistry in the engine room is the first step. To hit absolute zero, the external architecture of the ship must also change. Modern vessels are increasingly looking upward, harnessing aerodynamic systems to supplement mechanical thrust. These white cylinders are Flettner rotors. They spin rapidly, using the Magnus effect to catch crosswinds and generate forward thrust. Below the wind, the vast flat surfaces on car carriers are being covered in photovoltaic panels, capturing solar radiation to power internal hotel loads and navigation systems. As the hardware evolves, the software takes control. Global authorities are implementing the IMO MAS framework, establishing regulatory codes for autonomous, uncrewed surface ships. What you're seeing here is a digital twin. It is a virtual replica of a physical ship, updated with real-time sensor data from the vessel. This allows engineers thousands of miles away to monitor and simulate the ship's performance. By feeding that telemetry into AI routing algorithms, operators can dynamically alter a ship's course to optimize ocean currents and dodge weather systems, regularly saving over 10% on fuel consumption. The era of the purely mechanical merchant ship is ending. These new designs act as sensitive instruments, using real-time digital telemetry to adjust to their environment. Before these machines touch the water, they are born in the green shipyard. Computer-aided design translates directly into robotic welding, cutting steel with micrometer precision. When a ship reaches the end of its lifespan, its high-grade metals are dismantled and recycled into the next generation of the fleet. Independent classification societies oversee this life cycle. They enforce environmental mandates, requiring all newly built ships to meet carbon efficiency baseline standards before they are legally allowed to set sail. Once operational, their efficiency is tracked daily. This dashboard illustrates the carbon intensity indicator, assigning an annual letter grade from A to E based on carbon emissions. A ship continuously scoring a failing D or E grade can be legally banned from commercial trading until owners execute a mandatory corrective plan. Classification societies have turned zero-emission design into a legally enforced survival requirement for global fleet operators seeking to maintain commercial access. Despite these engineering advances, systemic obstacles remain. While shipyards can build methanol-ready engines today, the global network of specialized bunkering ports required to refuel them does not yet exist on a massive scale. Operators must also absorb the cost of synthetic green fuels, which trade at 3 to 6 times the price of conventional oil, while securing digital ships against cybersecurity vulnerabilities. Achieving complete maritime decarbonization will require a global investment of $1.4 trillion. The majority of those funds are needed to construct the land-based renewable energy grids required to produce the green fuels. The physical challenge of moving steel through salt water remains the same, but the machines are moving from diesel combustion to clean chemistry and digital autonomy, a shift that serves as the ultimate test of global economic cooperation.